So let's talk about the model in which we have a rigid body under constant angular acceleration. So in the past, we had an object moving with linear acceleration that was constant. Now we're going to see what happens when you have an object rotating with constant angular acceleration, right? So from the very definition of angular acceleration, we have is the change in angular velocity over time, right? So that means final velocity, initial velocity over final time minus initial time. If the initial time is 0, then you see the final velocity is the initial velocity plus acceleration times time, which of course is the angular equivalent to this equation that we studied in the past. Similarly, for the linear equation, let's say position final minus position initial, velocity initial, it would be 0, and then velocity initial time plus 1/2 of the acceleration times time. Well, the angular equivalent will be final angle or final angular position minus initial angular position, initial angular velocity, and 1/2 angular acceleration times time. Another one, final velocity initial squared minus initial velocity is delta 2a delta x. Well, the angular component, as you can probably guess, is just 2 instead of linear acceleration, angular acceleration, instead of linear displacement, angular displacement. Another one, final position minus initial position was 1/2 of the average velocity, basically. So same thing here. Initial plus final, right? So every single equation has a linear equation, has an angular analogous. So you can find this table in the book, and also in your equation sheet, you'll find the equivalent of each linear equation and angular quantities, linear equations, angular equations. So let's try this example. A wheel rotates with constant angular acceleration of that 3.5 radians per square second. They give us the angular speed of the wheel initially, and they want us to find the angular displacement. So we are here, we have all the equations. Let's see, we have the acceleration is given. We have the initial velocity is given. The initial time is given. They want to find the angular displacement, delta theta. This is what we don't know. And they're giving us final time as well. So what equation out of all of this work? Well, it's this one, 10.7. So the equation is theta final minus theta initial delta t plus 1/2 alpha delta t squared. So we know delta t is equal to t final because t initial was 0 is given, we're told here. So delta theta is initial velocity of 2 radians per second times 2 seconds plus 1/2 the alpha 3.5 radians per second squared times 2 seconds squared. So this gives you 4 plus 7, it's 11 radians. That's the angular displacement. We can convert this to degrees also. We can say 2 pi radians is 360 degrees, and that's going to give us 630 degrees, right? That's part A of this problem. Then there's part B that says through how many revolutions has the wheel turned during this time interval. So remember that one revolution is when the object, the rigid body, has rotated through 360 degrees, and that's the thing. Different, as this is different from linear motion. Here we have cyclical motion, so at every 360 degrees we start again, right? Every 360 degrees you start again. So you need to know how many revolutions you had. So this delta theta of 630 degrees, we can say that 360 degrees is one revolution, and this gives you 1.75 revolutions. The degrees cancel, so 630 over 360, and that gives times 1.75 revolutions. Part C asks, what's the angular speed at 2 seconds? So we can use this one. The final speed is the initial plus acceleration times time. So we started at 2 radians per second plus acceleration of plus 3.5. If the acceleration was negative, here we will put a negative sign, but this is, in this case, is positive. Radians per second square. The time final is 2 seconds. So seconds cancel, and I can add 7 plus 2, and that gives me 9 radians per second. So as you see, it's the same thing we did in chapter, I don't know what chapter, at the beginning of the semester, with a linear kinematics. So this is angular kinematics now. We will practice more problems in class, but this is basically the theory for angular kinematics.